Hello and welcome to a new video on classified physics, conservation of energy. This topic belongs to the unit of mechanics. So let's begin. Let's begin with the basic concepts. As energy is transferred into different forms, it eventually becomes dissipated. What does this mean? So the basic concept here is that the total amount of energy in a system is conserved. Energy is neither created nor destroyed. It is simply converted from one form to the other. So when we say dissipated, what does that mean? Does that mean that the energy disappears? No, it doesn't, because we said it's not created or destroyed. So A is obviously wrong. The energy changes into every possible form of energy. This is not true. It could change from one form to another. It doesn't have to change to every possible form of energy. The total amount becomes less is also false, because we said that it is not created nor destroyed. So basically, dissipated means it spreads out among the objects and their surroundings. For example, if a car is moving at a certain speed and then you press on the brakes, it slows down, so its kinetic energy decreases due to friction with the ground. And what happens then? The kinetic energy is transformed into heat energy that just goes into the environment, right? The heat dissipates into the air. So the correct choice here would be choice C. An object falls under gravity. What happens to the gravitational potential energy and to the kinetic energy of the object? So you might want to check our previous videos on kinetic and potential energies, as well as on the acceleration in free fall. If you are familiar with these concepts, you should realize that as an object falls, its potential energy decreases and it accelerates, so its speed increases, hence its kinetic energy increases. So the correct choice here would be choice B. Pendulum bob swings along the path W, X, Y, Z and back again. Resistive forces can be ignored. Which statement describes the total energy of the bob? This might be confusing because you might want to think, at X it has the lowest height, so the potential energy is smallest, but at W it's maybe starts at rest, so it has no kinetic energy, but has a lot of potential energy. All of this is irrelevant because no matter what the details of the energy are, the total energy has to be the same at all points because we said energy is conserved. So regardless of the fact that it has a lot of potential energy at W, more kinetic energy at X, and so on, these are like the components of the total energy. But the total energy stays the same either way. So the correct choice would be choice D. A toy car without a motor is moving at high speed along a track. The toy car follows a vertical loop as shown. Which row describes the changes that are taking place in the kinetic energy and in the gravitational potential energy of the car in the position shown? So in this position, it is moving down in a sense. So this is a repetition of a previous question. We said that the gravitational potential energy is decreasing and the kinetic energy is increasing. So the correct choice here would be choice C. Let's move on to more advanced concepts. A cyclist travels down a hill from rest at point X without pedaling. The cyclist applies his brakes and stops at point Y. What energy changes have taken place between X and Y? So since he starts at a higher altitude, in a sense, we can assume that he begins with gravitational potential energy. So we can immediately discard these two choices. What happens? He starts moving down and he's not pedaling, so he's not giving in any extra energy. It's just the potential energy that was in the bicycle begins to decrease as it moves down, and it's replaced with what? With kinetic energy. And then he stops by applying his brakes. And we said applying his brakes, that means that we get some heat or thermal energy. And that happens at the very end of the system. So when he stops, when he applies his brakes and stops, heat is dissipated into the environment. So it has to be a choice where heat is at the very end. And this makes the most logical choice anyway. He has gravitational potential energy at the top. He starts moving, so he gets kinetic energy. And then he applies his brakes, and therefore we get thermal energy. So the correct choice here is choice A. A stone of mass m is held at rest in water. The stone is released and falls vertically a distance h. The stone reaches a speed v. Some of the original energy of the stone is transferred to the water. As it falls, resistive forces cause the temperature of the water and the stone to increase. Which expression gives the work done against the resistive forces? So, like we said, energy is conserved. But how does that work out if we have resistive forces? So let's say we had some form of initial energy. It should normally equal the final amount of energy we have, excuse me. So under normal circumstances, initial energy should equal final energy. But what if we have resistance? Some of the energy is lost as maybe as heat to the surroundings or whatever. So in this case, the final energy becomes less than the initial energy because the initial energy becomes equal to the final energy plus some amount of work done against friction, against resistance, against air resistance or whatever. So in our case, the initial energy here is potential energy because it's held at a certain height and starts falling. So our initial energy here would be mgh. And our final would be the kinetic energy. And we said these are not the same. And we are interested in getting W. So W is simply mgh minus half mv squared. Does that make sense? I hope it does. So in a sense, work done against resistance or friction is basically the initial energy minus the final energy, whatever the form of the energy is. Hence, the correct choice here would be choice B. A car is stationary at the top of a hill with the engine switched off, the brakes are released, and the car rolls down the hill. At which point does the car have the greatest kinetic energy? Ignore friction. So ignore friction means that we're just playing around with either potential energy or kinetic energy. So conceptually, greatest kinetic energy means least potential energy. Why is that? Because the sum of the kinetic and the potential has to be constant throughout the entire problem. The energy is conserved. The total energy is conserved. So at A, B, C, and D, the total amount of energy is the same. So let's assume, for example, that it was at rest at this point, had potential energy of 10, for example, and the kinetic energy of 0 because it was not moving, and then it started moving. So maybe at A, the potential is 9 and the kinetic is 1, so that their sum is still 10. And then B is further down. So maybe the potential here is 7 and the kinetic here is 3. And we usually take the lowest point to have 0 potential energy, relatively. So the kinetic energy here would have to be 10. And then it starts moving back up. So here the potential energy maybe is 2 and the kinetic energy is 8. So at the point where we have the least potential energy, which is basically point C, we have to have the greatest kinetic energy so that the sum is always 10 because energy is conserved. So the correct choice here would be choice C. A ball is released from point X on a rough semicircular track. It comes to rest for an instant at point Y. The gravitational potential energy of the ball at X is EX. Gravitational potential energy of the ball at Y is EY. Which equation relates the energy at X to the energy at Y? This is similar to something we just did a couple of problems ago. We said that initial energy is equal to final energy if we ignore air resistance and friction. But if we do not ignore them, we have to have here work. And basically, instead of initial and final, we can just write x and y, and that gives us the answer. So the correct answer here is choice A. A skier walks from the bottom of a ski slope to the top and gains 10,000 of gravitational potential energy. She skis down the slope. At the bottom of the slope, her kinetic energy is 2,000. So at the top, she's at rest. So the potential energy here is 10,000 and the kinetic is 0. At the bottom, we always take the potential energy at the bottom to be 0. So they told us that the kinetic energy here is 2,000. And they are asking how much energy is dissipated in overcoming friction and air resistance as the skier moves down the slope. It's basically the difference between the two quantities. So that the correct answer is, logically, is 8,000 because it's 10,000 minus 2,000. It's the amount of energy she lost, because had there been no air resistance or friction, the energy at the top would have been exactly the same as the energy at the bottom, 10,000 and 10,000. But owing to the friction and air resistance, the total energy decreased. So the difference between them is basically the amount of energy dissipated. If we want to do this using our previous equation, we say EI equals EF plus W. EI is 10,000 equals 2,000 plus W. So again, W is the work done against resistance or friction or whatever, and this is equal to 8,000. So the correct choice here is choice B. The diagram shows the path of a stone that is thrown from X and reaches its maximum height at Y. The stone gains 10 joules of gravitational potential energy as it moves from X to Y. The stone has 2 joules of kinetic energy at Y. How much kinetic energy did the stone have immediately after it was thrown at X? Okay, so at X, the potential energy was 0 because that's the lowest point, and we do not know what the kinetic energy was. And then at Y, it gained 10 joules of potential energy. Excuse me. So at Y, it gained 10 joules of potential energy, and they say it had kinetic energy of 2. And since we are ignoring air resistance, so the total energy at all points has to be the same. And the total energy here is obviously 10 plus 2, which is 12. So the kinetic energy here is equal to 12, and the correct choice is choice D. Now that we've covered a lot of conceptual questions, let's go on to problems that require some math. An object falls from a height of 5. Air resistance can be ignored. As it hits the ground, the object has 750 joules of kinetic energy. What is its mass? Again, air resistance can be ignored. So basically, EI equals EF. EI here is energy due to height because it falls from a height. So this is basically mgh. And this is equal to the final energy, which is kinetic energy, which is half mv squared. Though we don't really need to write these two equations as such because we are given the kinetic energy as a whole. So instead of half mv squared here, I'm just going to write 750 joules. And we want to know the mass, so that's what we do not know. And the gravity is 10, of course. And the height here is 5. So simple calculation, m equals 750 over 10 times 5, and that gives us 15 kilograms. So the correct choice here is choice A. An object falls from the top of a building that is 25 meters high. Air resistance is negligible. What is the speed of the object when it hits the ground? This is the same question in a sense. Let's start by writing, since air resistance is negligible, let's start by writing EI equals EF. We do not need to add work done here. The initial is mgh. The final is half mv squared because it's the kinetic energy. Since it's the same object, I don't really need the mass. So this might actually look challenging to some of you because you do not have the mass. So how do you calculate? You do not need the mass because it's the same mass in both equations. So we simply cross out m, and g is 10, h is 25, equals half times v squared. So 250 equals half v squared. 500 equals v squared. So you just get the square root of 500 using your calculator. Just give me a minute. The square root of 500 is 22.36. And the correct choice here would be choice B. A car starting from rest at position X accelerates up a hill. The car reaches a speed of 10 at position Y. The kinetic energy at Y is equal to the gain in gravitational potential energy from X to Y. We want to know what the gain in height of the car is. So again, since we are given here, so did they mention that air resistance and friction can be ignored? Well, they did not mention it explicitly, but they did say that the kinetic energy is equal to the potential energy. So it's pretty much the same problem. Energy initial equals energy final. The initial energy at position X, excuse me. Oh, no, this is a different problem. I apologize. So this is an interesting problem. Yeah, I will explain some concepts. They won't really help you in solving this particular problem, but it's interesting to just understand better. Basically, the kinetic energy here is zero because it starts from rest. And the potential energy here is zero as well because it's at the lowest point in the problem. But they are telling us that the kinetic energy at Y is equal to the gain in gravitational potential energy. So if it has a potential energy of 10 at Y, then it has a kinetic energy of 10 as well. How did that happen? Well, because this is a car, it has a motor, right? So the car itself gives energy. When you turn on the ignition and you start driving the car, you're burning fuel, you're consuming fuel, and this gives the car energy. So it's okay for the car to start from rest and gain kinetic energy and gain potential energy as well, because all of this comes at the expense of what? At the expense of the fuel consumed by the car. So basically, it's chemical energy inside the car being converted into kinetic energy and potential energy. So this is not really a conservation of energy problem. It's just basically a kinetic and potential energy problem in a sense. The kinetic energy of the car is half mv squared, and this is equal to the gravitational potential energy of the car, which is mgh. And like we said, m and m can cancel out, but this is not a conservation of energy problem. It's solved exactly the same way, but it's not because of the conservation of energy in a sense. We're not equating kinetic to potential due to conservation of energy. They're actually both equal together to the chemical energy that was inside the car. But since they told us that the gain in kinetic is equal to the gain in potential, we can still use the same equation to solve. So let's substitute the values. We have half times 10 squared equals 10 gravity times h, which we do not know. So half times 10 squared, that's 50. That's equal to 10h, so h is 5. And the correct answer here would be choice B. The pendulum swings from P to Q to R and back to P. P is 10 centimeters higher than Q. At which speed does the pendulum bob pass through Q? So we assume here that the potential energy is 0, and we want to get the kinetic energy in a sense. And it starts from rest in a sense at P. At the highest point, we assume that the speed is 0. So the EK here in a sense is 0, and we want to get EP. So how do we solve this? Again, we just say mgh equals half mv squared. Cross out the m's. 10 of gravity times the height. You might make a common mistake here of writing the height as 10, but that would be wrong because this is 10 centimeters. So you have to divide it by 100. So the height is actually 0.1. This is equal to half v squared. 1 equals half v squared. We multiply both sides by 2. We just take this guy to the other side. So 2 equals v squared. So v equals square root of 2. And this is your answer, square root of 2. If you do that using your calculator, you are expected to get this value, choice C. Let's move on to more challenging problems. A ball of mass 1.2 is dropped from a height of 30. As it falls, 25% of its initial gravitational potential energy is transferred to thermal energy. What is the kinetic energy of the ball just before it hits the ground? So this is a bit tricky. It had a certain amount of potential energy, and as it fell, 25% became thermal energy. So how much of the initial energy was transferred to kinetic energy? Basically the rest. So 25% is lost as heat. So the amount of kinetic energy you have is 75%. 100 minus 25, pretty much. Excuse me. So the kinetic energy that the ball has before hitting the ground is 75% of what? Of the initial potential energy, which is what? Which is mgh. And we can actually substitute the values here. M is 1.2, G is 10, and H is 30. Now, using your calculators, you can compute the kinetic energy. This should give you 270 joules. So the correct answer here is choice C. A ball is dropped onto a floor. Its speed just before hitting the floor is 3 meters per second. Which change would result in a speed of 6 meters per second just before hitting the floor? Now, some people might just think this is double the speed. So to get double the speed, you need double the height. This is a mistake, unfortunately, because like we said, it's mgh equals half mv squared. So if you double the speed here, you get half m times 2v all squared, which is half m times 4v squared. So if we take this 4 outside, we get 4 times half mv squared. What does that tell us? That tells us that to double the speed, basically you need 4 times the amount of the kinetic energy. So you need 4 times the amount of the potential energy. Since the mass and the gravity do not change, you need 4 times the height. So the correct choice here is drop the ball from 4 times the height above the floor. Someone might wonder why D is wrong. Why don't we use 4 times the mass? Would that not work? It would not work, of course, because if you use 4 times the mass, yes, you are quadrupling the potential energy because you get 4m instead of m, but you're also quadrupling the kinetic energy as well. So it doesn't really change anything. You have 4 times the mass in potential, you have 4 times the mass in kinetic, and you still have double the speed. So these will not be the same. So you cannot use mass here. So the correct choice here would be choice B. This is pretty similar. A steel ball is fired vertically upwards with a velocity v. The ball reaches a height h. Now the same ball is fired from the same position with a velocity of 2v. Like we said, 2v squared gives us 4v squared. So we are expecting to get 4h. So the correct choice here is choice C. An object initially at rest is dropped from a height of 12. The change in gravitational potential energy is 565. What is the speed when it hits the ground? So the interesting thing about this problem is that they gave you this number, which you could use or you could not use. And not using it is much faster and much more efficient than actually using it. So I'll solve it both ways so that you get a feel of the difference. So here is what happens if we try to use it. We say that the potential energy is mgh, and 565 is equal to m, which we do not know, times 10 times 12. Now we can get m. So m is 565 divided by 120. And you use your calculator. 565 divided by 120, which is roughly 4.71. And then since energy is conserved because friction is negligible, they said here friction is negligible. So we know that the kinetic energy is 565 as well. And this is equal to half mv squared. And we got the mass already as 4.71. And we want to get v squared. So you multiply 4.71 times 2. And that gives you 9.42. And you do 565 divided by 9.42 equals v squared. And then you get the square root of this fraction. So you end up with v equals 565 divided by 9.42 gives us 59.97, roughly 60. And the square root of that is, oh, I made a mistake. I'm sorry, I made a mistake. No, so it's the half. I multiplied this by 2 instead of by half. So this is not 9.42. I apologize. This is half times 4.71, and that gives us 2.355. I apologize for that. And then instead of this, we have to write 2.355 as well. So what we do here is 565 divided by 2.355, and that gives us 239.9. And then the root of this answer is 15.5. So we get V equals 15.5, and the correct choice is B. But this is a very inefficient way of solving the problem. As you can tell, I made a mistake in the calculations and things got very messy, and I didn't need to do any of this. So in red, I'm going to solve this problem in another way that actually ignores this number altogether and doesn't use it. Because similar to what we've done before, we know that the frictional forces are negligible. So we can just say half mv squared equals mgh. And then we cancel out m and m. So half v squared equals 10 times 12. So half v squared equals 120. And that tells us that v squared equals 240. And then you just get root of 240. And that gives you the same exact answer. Much simpler, much nicer, much cleaner than what we did before. So even though they gave you this piece of information, using it would have been very messy for no reason. As you can tell, when we're dealing with conservation of energy, it's just easier to write the equations and cancel out the mass. This concludes our video. I hope you found this beneficial. See you in the next one.